So I guess we can start today's seminar for Geometry, Algebra, and Physics at KIAS. Today's speaker is Professor Rinat Kashaev at University of Geneva. He is going to talk about applications of the quantum dilogarithm. And before starting, I would like to thank him especially because he was willing to give a talk in the early morning in his time, which is 6:30 a.m. So let's welcome him.
Thank you, Hyun. Thank you for invitation. I'm very glad to give this online talk. So my talk is in the first part. At least will be some review talk about applications of the quantum dilogarithm, which is a special function uh, which finds numerous applications in mathematics and mathematical physics. And here is an outline. So I start from classical dilogarithm. So the quantum version of it is a certain deformation in the way, so it will depend on the extra variable. The way usually we have a quantum quantities like wave functions, which behave singularly at when Planck constant goes to zero. And then I'll describe, but of course I'll give a couple of applications of a classical dilogarithm, and the main part of my talk will be about applications of the quantum dilogarithm, namely um, in lattice integrable systems, spectral theory, and quantum topology. And then I will turn to generalization of the quantum dilogarithm to the context of locally compact abelian groups, and try to describe how at least one application on the level of representations of the of mapping class group of punctured surfaces, which is in a sense it's a halfway to a three-dimensional TQ of T. But in this part, I will describe a TQFT, but not will go that far for general more general examples of the quantum algorithm in this context of compact abelian groups, locally compact abelian groups. Okay, so the classical dilogarithm is defined through this infinite series, which converges in the unit disk. But it can be analytically continued through this integral formula. And the remarkable properties of it are given by, two lines. Maybe this line not very exciting, just some symmetry property, but the second line is more interesting because it is a non-trivial identity, a five-term identity, which underlies many applications of this function, which is called Rogers five-term identity. And actually, so the Euler dilogarithm, which was index 2 here, and this L of x, they differ by this elementary function addition, which is also called Rogers dilogarithm. And then you see that this is a functional equation with two independent variables and x, y. But to avoid, you should avoid these zeros in the denominators to make sense of it. And the one application of the classical logarithm is in geometry, namely famous Milnor's formula gives a volume of ideal hyperbolic tetrahedron in a three-dimensional hyperbolic space. So the up to isometry, any ideal hyperbolic tetrahedron is characterized, for example, by dihedral angles along its edges. So here I try to draw a three-dimensional tetrahedron. And the dihedral angles are given just by Euclidean tangent planes along the edges of this tetrahedron, because the faces are given by Euclidean spheres. And so the angles play, at each vertex, the angles sum up to pi. And this comes from the fact that for any ideal hyperbolic tetrahedron, one vertex can be sent to infinity. For example, in the upper half plane, half space model, when one vertex at infinity, then the faces which meet at this vertex, for example, if this is at infinity, these faces become vertical Euclidean planes in the upper half space model, so that this triangle projects to Euclidean triangle at the plane z equals 0. And so the dihedral angles become Euclidean angles of this Euclidean triangle. So this explains this sum rule. And then the volume of this ideal hyperbolic tetrahedron is calculated as a sum of three Lobachevsky functions, where Lobachevsky function is up to multiplicative factor 1/2, is the imaginary part of the Dilogarithm function where the argument is put on the unit circle through this formula. And I'd like to mention another application of the classical Dilogarithm, but this time through the real part of the function evaluated at the same value on the unit circle. This time the real part is just elementary function, but it is periodic function, as it can be seen from the series formula. So it is a function of period pi. And so this equality gives us a summation formula for the left-hand side. And this summation formula allows to prove completeness in many orthonormal for many orthonormal systems in separable Hilbert spaces through Parseval's equality. Okay, now I'm turning to quantum dilogarithm. So the quantum dilogarithm is a special function of two variables, b and z. This is a so-called Faddeev quantum dilogarithm because there are a few different versions of it. And it is given by exponentiated integral, Fourier integral, actually, where the singularity at the origin is put below the contour of integration, which is reflected in this prescription that we go, the singularity is put below the contour of integration. This. And it satisfies a number of properties, namely pair of functional equations, difference functional equations, and also some symmetry properties with respect to variable b, which are manifest actually from this definition, namely invariance and the b inverse, as you see here, and then also invariance and the negation of b, which is also seen here because we have a odd product of two odd functions, and so the product is even function in b. As a result, we can put this variable b in the first quadrant with strictly positive real part and non-negative imaginary part. But I should point out that the pure imaginary axis should be avoided to make this function well defined. While pure imaginary axis is very singular, as can be seen from this formula, because sinh function becomes a sine function with infinitely many zeros, which become poles of the integrand. And as a historical remark, the special case of this function when b equal 1 was studied by Hölder back in 1886. He wrote this infinite product formula, from which you can see all the location of all zeros and poles. And the connection between this Hölder product and the function phi bz is through this formula. So you here b equal 1. So the equality is up to a simple Gaussian exponential in x. Even more, this phi 1 function itself can be expressed entirely in terms of the classical Dilogarithm function through this formula, which is to me is a remarkable equality, because classical Dilogarithm is a multivalued function in the complex plane, while phi 1 through this Hölder's equality is a meromorphic function. So it is single valued with multiple poles, but there are no more sophisticated singularities. So this means that this exponentiation removes all these branch cuts of the classical Dilogarithm and produces a meromorphic function. Okay, now here I list a few properties of the quantum Dilogarithm, among which I highlight two of them as the important properties, which are here. So the first important property is a property I call inversion relation, which just says that if I multiply phi b of z with phi b minus z, I get just a Gaussian exponential, oscillating Gaussian exponential, up to a constant in front, which is given by this explicit function of b, which is a particular carries all the symmetries which I mentioned. So it's a symmetry with respect to inversion of b and the negation of b. And the second important property is five-term operator identity in the Hilbert space of square integrable functions on the real line. So here I insert in the arguments of the function Heisenberg operators. Q hat stays for the just coordinate multiplication operator, and p hat stays for the differentiation operator. We know that in this space, these two are self-adjoint operators with a spectrum given by the whole real line. And the third property indicates that the Faddeev's function it takes its values on the complex unit circle, which means that all five operators, or three operators which enter in this identity, are unitary, because the arguments effectively are real due to self-adjointness of these Heisenberg operators. And as you see from here, Z bar is Z. For Q bar, we are on the complex unit circle. So this is a perfectly well-defined operator identity for unitary operators. And this is one of the most important properties which underlies the applications I'm going to talk about. Okay, so yeah, so the unitarity is true when this combination of B is real. So in particular, if B is real, or B itself is on the complex unit circle. So you see, if B is a pure phase, then this is a trigonometric cosine function of the argument of B, which is real. And another property allows to identify all poles of phi B. So for generic B, all poles are simple, and actually they are given by a sector of regular lattice. So as you can see, the integers mn run over only positive values. So so if B, for example, is on the unit circle, so you have a vector B like this, and the vector on B inverse like this, and then you see that the poles are located on this quarter sector of lattice points. But if if B approaches a real value, then this sector shrinks to a half line, and then the poles become multiple poles, but of finite multiplicity, and in particular for B equal 1, they become just the poles of a Hölder function concentrated. You see the multiplicity grows when we go further away from the. But here remember that the Hölder's x and the variable of phi1 differ by imaginary 1. So this is why here you see the poles and zeros on the real line, while for phi b, for phi1, it will be the imaginary line. And of course, this formula gives poles, but the inversion relation immediately tells us that the negated those values correspond to zeros, because this formula tells us that they cancel out. And why we call it quantum Dilogarithm, the explanation is given by this asymptotic formula. So if we rescale the argument by B like this and send B to 0, then the behavior is a typical quasi-classical behavior in quantum mechanics. So the B squared gets into the denominator, and the numerator is some quantity independent of B, and which is essentially given by the classical Dilogarithm evaluated at this argument. Now let me start talking about applications. And I start by applications in two-dimensional lattice integrable systems. So I'm going to talk about the so-called Fadeev-Volkov spin models, which some infinite state generalization of the famous Ising model, because they characterized by two spin interaction weight functions. And the definition is as follows. We just take a ratio of two Fadeev functions. So we have two new independent variables. But for interpretation in terms of statistical mechanical models, we just choose from one hand side, the variable x we choose to be real, but the second variable to be purely imaginary on the negative part. And in this case, this combination is the absolute value of this function squared. So it is a positive weight function, which makes sense of Boltzmann weight of a certain spin model where spins take values on the real line. And actually, we are going to put differences of two spins, and we are going to interpret them as an interaction of two pair of spins. And and why this model is remarkable? Because it is integrable in the sense that this weight function satisfy a version of the Yang-Baxter equation, which is called the star triangle relation, which is written here. And why star triangle? Because it can be drawn as a kind of a star triangle. So we have two spin interaction weights, and for example, the right-hand side is a product of three interaction weights given by these three weight functions, while in the left-hand side we have product also of three weight functions drawn here, but integrated over the central spin. So the central spin corresponds to the variable t, which enters all three. Yeah, so here I'm using a W tilde B, which is just the Fourier transformation of this function with respect to the first argument, which is the result. Another remarkable property of the Fourier function is that the Fourier integral of this kind is calculable in terms of the same function. So you see it is the same function, but with some shifted second argument times some multiplicative factor, which is defined still in terms of the same function and some elementary multiplicative factor. Okay, so this is the Fadeev-Volkov model, and here I want to remark that as a side product, this weight function produces a Fourier stable, strictly positive Schwarz functions. So the most famous of them is this Gaussian exponential, less known but also still well known inverse Cauchy function, which is also stable under Fourier transformation. And the formula for the Fourier transformation here allows us to add infinitely more members into this family through this formula. And for rational values of b squared, these functions become actually the elementary functions through this Pochhammer product combinations. And here I list a few simplest examples. For example, when mn here both I equals 0, we reproduce this the function, which is Fourier stable. But if we go further to some less trivial values of Mn with the corresponding values of B, and this symmetric combination at the B. Remember this at the B was B plus B inverse half. Then we recover some more sophisticated elementary functions which happen to be Fourier stable, like this, like this, and so on. So, actually, we have infinitely many of them indexed by two integers. And this is a quite non-trivial fact because of strict positivity. If we don't impose the strict positivity, this is not big deal to create Fourier stable functions because the force power of the Fourier transform is identity. So we can take any function and average it with respect to the different Fourier transforms. But there is no guarantee at all that the result will be strictly positive functions. So this is a non-trivial part of this remark. Now, second application in the context of 2D lattice integrable systems is the following observation. So we can take a so-called Weil-Gelfand-Zach transformation, which essentially consists in the following. So we take the first argument. Remember, in the Faddeev-Volkov model, this was corresponding to local states of the model. So what we do, we translate by an integer and interpret the result as a Fourier coefficient of a periodic function. So we just write a Fourier series here with respect to this coefficient. So we introduce new variable, and then we slightly correct the result by an elementary function. So the result is that is a double periodic function in these two variables. So the former variable x becomes, before adding this multiplicative factor, we get just a periodic, sorry. So first, with respect to this new Fourier variable, it is manifestly periodic. But with respect to the former variable, it is also almost periodic, but not quite. And effectively, by taking into account this extra factor, we have a quasi-periodic function. So you see, if I translate x by 1, then up to this exponential of u, it is periodic. And likewise, but before multiplying by that, it was a periodic in U, but this factor spoils a little bit the periodicity, so it also becomes a quasi-periodic through this formula. So it is kind of symmetric now, as you see. The shifting U produces quasi-periodic function, quasi-periodic factor depending on x. Likewise for x, shifting x produces a quasi-periodic factor in U. And this is the reason why I'll multiply it by this becomes because the quasi-periodicity becomes very symmetric up to a sign here. And then the star triangle identity, which was here, is transformed to another identity, which is much more symmetric. So it is an integral identity where both sides are very similar. So you have a product of three functions m integrated over one of the two variables we are produced by the transformation. And as a matter of fact, you can check that the product of these three is periodic in T. I mean, all quasi-periodicity factors cancel out. And this is why we integrate just over the period of this function here. Likewise, in the right-hand side. And this identity now it can be interpreted as a the IRF version of the Young-Baxter equation. So here I give a graphical interpretation of it. So I put so-called rapidity line axis here, which carry variables, spectral parameters alpha, beta, and then everything, and 4 state variables on the regions obtained by dividing the plane by these rapidity lines. So index I, A, B, C, D, and I put some differences into the arguments of the M function. So, and then the integral identity in here becomes a Young-Baxter equation of IRF type, where we take products of three squares and integrate over common internal state variable g here, like was here, and then we have a equality. So this is a famous IRF form of the Young-Baxter equation, so which still gives an integrable model, but this time these are not necessarily positive weight functions, but algebraically it is a kind of nice algebraic structure. Okay, now I'm turning to another application, this time application in the context of three-dimensional lattice integrable systems. So for this, let me just make a little preparation. So for any function taking non-zero complex values with arguments real numbers, I associate an operator like this. So remember, this P and Q are just Heisenberg momentum and position operators, which are self-adjoint. So in the spectral sense, the argument of F is just a real number given by spectrum of Q tensored by 1 and 1 tensored by P minus Q. So P minus Q is still a self-adjoint operator, corrected by some exponential of these Heisenberg operators. So they act in the tensor product of this L2 space, which can be thought as a, of course, it is some kind of completion of the tensor square, so which can be thought as a L2 of R squared. And then with this auxiliary operator S, we take this combination. So 1, 3, 2, 3 stand for for identification of tensor components. So this operator lives in X in the L2 of R cube. So this is why we have indices 1, 2, 3. So P is just the permutation operator, which exchanges two arguments, and S 1, 3 means that S 1, 3 acts as this S with respect to variables 1 and 3 in this R3, but do not touch R2. So this combination, so it acts in this space, which I highlight also here. And it solves Zamolodchikov tetrahedron equation, which is the analog of the Young-Baxter equation in 3 dimensions. So this is a nonlinear identity, which is in the L2 of R6, because we have here 1, 2, 3, 4, 5, 6 components. And it solves the Zamolodchikov tetrahedron equation under the condition that the phi and psi, which enter here, satisfy this operator form of the pentagon identity. So in particular, we can take for phi b, and for phi b prime, where it's generically we don't need to keep the same b. So in this sense, we have an integrable for the three-dimensional integrable system indexed by two different parameters. So in this sense, quite a rich model. Okay, so now one more application of the quantum algorithm in the spectral theory. And this corresponds to following observation. So if we take this, just think that B is real. Then here I wrote a sum of two positive self-adjoint operators, because these are self-adjoint, so their functions, yeah, in particular exponentials, are also self-adjoint, but due to the property of the exponential, it is a positive self-adjoint operator. And the sum of two any positive self-adjoint operators is self-adjoint, which means that we can ask for the spectral problem for this operator. And then the pentagon operator identity for phi implies that this operator can be obtained by unitary conjugation of a single exponential operator, of the position operator. So in a sense, so this equality solves the spectral problem for this operator, because in the middle we have a multiplication operator already conjugated by this U operator, which is written explicitly here, and it is unitary when B is positive. But along this equality, so we have also another equality. So you see that this operator and this operator commute because they depend on one and the same position Heisenberg operator, which means that these two also commute, and even more, they are simultaneously diagonalized, because they diagonalized by one and the same unitary operator. So in a sense, this is a function of this one. And also, given the fact that we can put here either variable b or its inverse, so we have explicit manifestations of Faddeev modular duality. So these functional identities implement that we have this functional identity. So this sum with positive exponents here raised into this real power becomes a sum of the same exponentials, but with inverted b. In a more compact way, where we can state that u hat plus v hat at power tau is just the naive way of expanding the binomial formula, just putting the powers to the summands, where tau is b squared. And so I change a little bit the interpretation of this identity, but it is the equivalent form of it. With this UV, which are just commute like Veil type operators, like this. Quite a remarkable identity. And another spectral application is given by the following observation. So if we define a map from L2 of R to L2 of R positive with specific integration measure, then this is a unitary equivalence. It becomes a unitary equivalence. So the kernel of this transformation is essentially given by this Faddeev-Volkov Boltzmann weight, but this time now this time we interpret a little bit differently the arguments x and y. So as you see, the first argument is just the integration argument, while, sorry, first argument is the output argument in the integral kernel, while the second argument shifted by some imaginary quantities is the integration argument in this integral operator. And so this unit, as I said, it is a unitary operator, and then the conjugation by this unitary operator of this multiplication operator. Remember that this q has still the position operator, but put into the context of half positive line. Okay, so because we are in this space now. But the result is a three-term operator. So cosh is the exponential plus so exponential sorry, exponential q hat up to some coefficient plus exponential minus q hat. So this two-term identity and plus exponential of the position operator. And so this formula tells us that this three-term operator can be diagonalized by using this unitary operator V, and yeah, and also some kind of modular Faddeev's modular duality property given by this identity. Okay, so I stop here talking about spectral applications of the quantum dialog, and then now I turn to application in quantum topology. So how we proceed? So am I going to talk one non-stop 1 hour and a half, or we make a break? I don't know.
Well, non-stop is fine.
Yeah, okay. Uh, application in quantum topology. So it is I'm going to talk about this so-called Teichmüller TQ of T. So which is a kind of model for quantum 2+1 gravity with negative cosmological constant. So it is it dates back to 2014. The work done in collaboration with Johan Andersen. And so the combinatorial part of the model is based on ordered delta complexes of Hatcher. So what is a delta complex? So it is just a CW complex where all simplices are given by standard simplices. So this is a characteristic map of a cell, n-dimensional cell. And the standard simplex carries a number of extra properties. For example, it has phase inclusions. So one-dimensional smaller standard simplex can be included as a facet of the n-dimensional standard simplex through this formula. And the particular property of the delta complex is that if we restrict a characteristic function of an n-dimensional cell to its ith facet, then we obtain a characteristic function of another cell of one dimension less, which I denote the di of alpha. So this is the most important property of the delta complex. So we can think of order delta complex purely combinatorially in terms of sets of n-dimensional cells and the phase maps, which associate to each n-dimensional cell its n-1 dimensional facet which satisfies the standard boundary identities, or for simply shell complexes, for example. And here is the example, simplest example of a order delta complex. Namely, we can represent three-dimensional sphere as an order delta complex consisting of one single tetrahedron. So you see the set of three-dimensional cells is just one element. But the four faces of this tetrahedron are pairwise identified by respecting the arrows on the edges. So, for example, this face gamma is identical to this face gamma. So this the identification goes like bending the tetrahedron along this edge and closing up like a book. So this vertex gets identified with this vertex. This edge gets identified to this edge, and this edge to this edge. And the two remaining faces also are identified, but visually it is less evident how it goes, but still the principle is the same. You should identify the faces the way that all oriented edges get, all orientations are respected. And here the formal identification. So you see we have four sets of cells of the corresponding dimension. So in particular, we have one zero-dimensional cell, one vertex, two edges, uh, two faces, and one three-dimensional cell. And all of them are indicated here in this picture. And for example, uh, the facets of alpha, zeroth facet and third facet identified together give the cell beta, the face beta. Likewise, 1 and 2, which give gamma, and so on. Edges and so on. So this is the example. As you see, it is quite economical. So the three sphere is encoded combinatorially this way. And the finite order delta complex representing an oriented pseudo three manifold is called a triangulation. So then we have two types of oriented tetrahedra, and the positive and negative. So the principle is simple. We put a minimal vertex in the center, next minimal to the top, and then vertex 2, 3 can be 2 to the right, 3 to the left, or vice versa, 2 to the left and 3 to the right. Depending on this, we call the positive and negative. So we have a sign function. And then to define the model, we add a shape structure, which corresponds to assigning a structure of ideal hyperbolic tetrahedron to each three-dimensional cells of the triangulation. And I already mentioned the ideal hyperbolic tetrahedra described in terms of dihedral angles. But this time now we play with these angles on the global level. So when we glue the tetrahedra, then we add the dihedral angles along the common edges. In particular, the internal edges get some sum of dihedral angles coming from individual tetrahedra. And we say that this edge is balanced if this total angle is 2 pi. If all edges are balanced, then we talk about the angle structure. And as a side remark, so the unbalanced edges corresponds to conical singularities, modeling the world lines of massive point particles in 2+1 gravity. But if they are balanced, so they are kind of invisible, they're non-existent edges. Yeah, and then so in the space of shape structures, there is a gauge transformation generated by total dihedral angles around internal edges via the Neumann-Zagier-Poisson bracket, and shape to three Pachner moves preserve these gauge equivalence classes. But to be able to apply this to three Pachner move, we need that this internal edge is balanced. Otherwise the move is not applicable. So this is the main topological property of the model. And then we now uh, realize the model by assigning certain weights to combinatorial data. So with this notation, we assign we color all two cells by real numbers and associate uh, to each so the y is a color of a tetrahedron, and x is a color of each triangle. So one tetrahedron has its own color, tetrahedral color, and the four colors around the associated with four faces, or four triangles on the boundary. So we have four of them, and we associate to this weight function, which is a distributional value. We have four phase variables, x0, x1, x2, x3, and the variable associated to the tetrahedron itself. And we have some topological restriction for the triangulation, which we call admissibility condition. And then the so-called kinematical kernel is the product of all those weights integrated over two-dimensional over the variable sitting on the on triangles. So the result is certain distribution, tempered distribution associated with variables sitting in tetrahedra only. And then second thing, we define the dynamical content, which assigns this weight function to each tetrahedron. So the remember, this is assigns a real number to each tetrahedron. And this is in variable y, it is a Schwarz function because of the properties of this the whole function. We have some angle variables, uh, and we have a sign variable depending on the whether the tetrahedron positive or negative, and we take just the product, and this we call a dynamical content. And then the partition function is just the pairing of the uh, tempered distribution with this test function. We get a scalar, and then a theorem tells us that the absolute value of this quantity is invariant under shape gauge transformations, shape 2-3 Pachner moves, and all orientation reversals on the edges. So essentially, the ordering of the delta complex doesn't matter. So essentially, we get the topological invariant of the complex. And here is an example. So it is the same one tetrahedron delta complex of three sphere, which I mentioned earlier. So we have two geometric edges drawn in blue and black. But the point here is that we cannot balance all edges simply because of the assignment of dihedral angles to which correspond to ideal hyperbolic tetrahedron. and this angle rules prevent us of from balancing all edges. So the best we can do, we can assign certain total dihedral angle to one edge, and then automatically the total angle on the another edge will be 2 pi minus that alpha. So the result will be function of this alpha. The gauge transformations correspond to shifting the on the tetrahedron. We have remember we have three angles which sum up to pi, and the gauge transformation means that two of them we can shift arbitrarily, but of course keeping the total sum to be equal to pi. And so the result, the alpha is only gauge equivalence, gauge equivalent quantity. So as a manifestation of the previous theorem, so the partition function is a function of only this alpha, and here is the explicit answer for this partition function. And in physical terms, as a partition function in 2+1 gravity, this should be thought as the amplitude of a space-time with two walled lines of massive particles which carry the deficit angles like alpha and 2 pi minus alpha, and which interact topologically in the space. In particular, you can think of S3 as a R3 with point at infinity, and this single vertex of this complex you can put at infinity. Then two edges become two long knots which come from infinity and go to infinity, and in the finite part they somehow interact. As a matter of fact, this blue edge happens to be knotted like a trefoil in the finite part of the space, while a black line is not knotted, but they linked with each other still in certain way. So we have an example of an interacting massive particles in this model of 2+1 gravity. Okay, so and then to finish this part, I want to mention the volume conjecture for this model. We can associate to any configuration of shape triangulation the volume just by maximizing the sum of individual volumes of tetrahedra staying inside the one equivalence class, gauge equivalence class of angle assignments. So if we define this maximum as the classical volume, then the volume conjecture tells us that this asymptotic limit when b goes to 0 gives a minus this classical volume. And this is confirmed by now in a number of cases. So for knot complements, for 1 and 5.2, it was done already by Anderson and myself back in 2014. Subsequently, it was confirmed for 6.1 by Anderson, Kratman, Nissen in 2017. Then it was proven for an infinite family of twist knots by Benaribi, Girito, Piki, Nakazawa in 2023. And Piki Nakazawa also checked it for few knot complements in RP3 in 21 in his PhD thesis. And then very recently, so Benaribi Wong and Benaribi Yellow Wong proved it for a very large class of so-called finite triangulations. Yeah, so that if you are interested, you can look the papers. So the very impressive result, and these authors just check it on the census for thousands of different concrete examples. So this is really works this volume conjecture by now, but still, of course, not proven in general. Okay, now in the remaining time, I want to turn to generalizations. So generalizations to locally compact abelian groups. Um, so let me make some preparatory work. So by T, I denote the unit complex circle. And the Gaussian, what is a Gaussian group? Gaussian group is a Pontryagin self-dual locally compact abelian group equipped with a Gaussian exponential, which is essentially a non-degenerate quadratic, multiplicative quadratic form with values in this abelian group, which means that it is symmetric, and this combination gives a non-degenerate bicharacter, which is an equivalent of a bilinear form if we write everything additively. And we also fix the normalization of the harm measure by this condition with respect to this bilinear or bicharacter, which I will call a Fourier kernel. And yeah, so already for Gaussian groups, we can talk about certain 4D metaplectic TQFTs where we define 5-index objects which can be interpreted as the weight functions of 4-dimensional simplices in this 4D TQFT, which is given by this Gaussian and the Fourier kernel of certain combinations up to some scalar factor, which is this kind of improper integral. And here are a few examples. So this is a basic example, the real line with the usual Gaussian exponential, where the Fourier kernel is just the usual Fourier kernel. And then less evident examples. We take complex unit circle times its Pontryagin dual, the group of integers, and the Gaussian exponential is just the pairing, natural pairing between two dual objects like this. And a more sophisticated example, the p-adic completion of rationals. Then we have an analog, because the real line also a completion of the rationals. But for p-adic completion of rationals, we have an analogous Gaussian exponential, which uses the p-adic fractional part. So if you use just the usual fractional part over reals, then you get back to this formula because the exponential is 2 pi I periodic. So only the fractional part of x squared half matters. And this naturally generalizes also this to p-adic completions. And then we define quantum dilogarithm over Gaussian groups. So that we need a Gaussian group, means self-contracting self-dual and the Gaussian exponential. And a quantum dilogarithm this is the most general definition up to date. So it is a tempered distribution on A represented by a locally integrable, almost every way defined function phi, which satisfies two identities. Remember, when I was listing the properties of a function, I highlighted two properties as important. So these two important properties I put as a basis of this generalized definition. So the inversion relation. This time we replace the usual Gaussian exponential by this Gaussian generalized Gaussian exponential up to a constant. And the 5-term identity, which I write here not in operator form, as just as a triple integral of product of three phi's with this kernel, which is a 5-index object, which I defined previously here in the context of metaplectic for the TQ of T. So it enters here as the integration kernel. But integration should be thought in proper sense as a distributional integral identity. So this should be thought as a distribution of on two variables, and here as a distribution of three variables, and a certain push forward of distributions through this integration. So this defines a general notion of quantum dilogarithm. And then we can reformulate all this in operator language. So if we have such a quantum dilogarithm of a Gaussian group, as in the previous slide, then we can define a Fourier transform, because we can apply Fourier transform to the temporal distributions. And then, so this defines as, sorry. So, here I'm talking about operators in L2 for the moment. So we have a unitary Fourier transformation operator in L2, defined by this formula. And then I talk about multiplication and shifted momentum operators, which are which you've seen already in the context of L2 of R. But here we should be more careful, because the Q hat is not defined just by itself. We can define it only through the argument of some complex valued function. So if we put a function g complex valued on A, then we can talk about multiplication operator. And this multiplication operator, I denote just the g of q hat, which is a formal notation, but the meaning of it is just this multiplication operator. And then the shifted momentum operators are defined through unitary conjugations of the multiplication operator. So I take it here, and I conjugate it by Fourier transformation operator, which is a unitary operator. Then I take a Gaussian exponential, which has its values on the complex unit circle. So if I put the argument q hat in this sense, then I get another unitary operator. I can raise it to nth power for n an integer, and conjugate by it this operator. So this way I obtain g function, the shifted momentum operator, but still through application of arbitrary function. And then the pentagon identity still can be written in this operator form, which you have seen for Faddeev function, but now it makes sense in this more general context. And now and here are a few examples. So here are a few examples. This is a prototypical example of Faddeev dialog. So in this context, so Faddeev dialog gives an infinite family, one parameter family of examples, because the parameter b is fixed. And here another example where the locally compatible group is taken R times a finite cyclic group. And then the Gaussian exponential is a Gaussian exponential in first argument times a Gaussian exponential in the finite part. So here, coming back to this list of examples, probably Gaussian groups, I can add maybe any finite abelian group. So any finite abelian group is self-dual in Pontryagin sense, and then you can interpret as a Gaussian group. But the quantum dialog cannot be defined in the form I defined for finite groups, but finite groups can be combined with infinite groups like this. And then we have a Gaussian exponential, and here is a quite complicated quantum dialog given by a product of n Faddeev dialogues with some sophisticated arguments. The essential thing is that so this x now is a pair of elements, real number and then an integer modular capital M. And then so this x appears through this first component t and the second component m. So in M in particular, it should be capital and periodic as it is because this is a fractional part actually. This is a fractional part. Yeah, another example on T cross Z. Again, X is a pair Z and M, and the Gaussian exponential like this. And the quantum dialog is a ratio of two infinite Pochhammer products. Here I assume that Q is inside the unit disk. Again, this is a here we have a family of quantum dialogues because if we index by Q. Likewise in the previous example. And an example which I like a lot, so it comes from local fields. If you have a local field, you consider the subset of non-zero elements of this local field as a multiplicative abelian group. And then you take its Pontryagin dual, and then the quantum Dilogarithm is this simple evaluation. This time it's not defined everywhere. It is not defined for a equal -1, so it should be excluded. But it perfectly fits into the definition I gave because if you remember, I required that the function should be almost everywhere defined. And for local fields, singletons are negligible. So we can not worry about that at one point it is not defined. And just to conclude, let me talk about representation of mapping class groups. And as a preparation for mapping class groups, I'd like to define so-called the basic algebraic system, which is the following thing. So we take a vector space V and pair of operators called capital R and capital T acting in V and V tensor V. And we require three properties. R should be order 3, pentagon identity for T, and certain compatibility condition for R, T, and also the permutation operator which enters into this last relation. Lambda is just some non-zero constant. And just to be to recall you the meaning of notation. So T1, 2 is T put into first two components in this triple tensor power 2, 3 in the last two components. 1, 2 we just conjugate by permutation by T1, 3. So effectively this conjugation replaces this 2 by 1. Okay, so this is the basic algebraic system. And then a quantum dilogarithm, which I just defined of a Gaussian group, allows to realize this basic algebraic system through this formula. So remember that this is a Fourier operator. This is a multiplication operator by the Gaussian exponential. This is just a constant function. Remember this gamma A was integral of the Gaussian exponential. And T is this momentum position operators shifted by -1, so which I was defining in the previous slide, and some Gaussian exponential with the tensor product of arguments. So this is T and R. So this is the basic algebraic, realizes the basic algebraic system. And why we are interested in basic algebraic system? And the reason is the following. So here I'm now talking about mapping class groups of punctured surfaces. So what is the setup? So we start from S bar, which is a closed oriented surface of genus G. Then we specify punctures, which is just a finite subset of this S bar surface with R elements. And then the punctured surface is a complement of this finite set in this S bar. So we also put sub indices G and R to recall that we have a genus G and R points removed. So this is our S, and we require that set of punctures is non-empty, this strict inequality, and that the Euler characteristic of this surface is strictly negative. Strictly negative, and why these conditions? And the reason, one of the reasons, is that such surfaces admit so-called ideal triangulations. So what is ideal triangulation? It is just the CW decomposition of this closed surface with this finite set as a zero skeleton or the vertex set, and all two cells are triangles. And then we talk about decorated ideal triangulation if we fix a linear order on the triangles, for example, by enumerating them from 1 to and so on, and choosing a marked corner in each triangle. And then we denote delta S, the set of all decorated ideal triangulation up to isotopy. And the mapping class group, which is a quotient group of the orientation preserving homeomorphism of our surface S modular homeomorphisms in the connected component of the identity, then this mapping class group, MCGS, freely acts on this set of decorated ideal triangulations. And why this free action is important? Because we have a very general construction of a group point from a free group action. So if a group freely acts on a set, then we can associate the group point GE as follows. So the set of objects are G orbits in the set. Set of morphisms are G orbits in the Cartesian square of the set modulo diagonal action. And then, so we have a domain map. So if we have a orbit of a pair of xy, then the domain is a orbit of the first component, and the codomain is the orbit of the second component. And then two morphisms are composable if the orbit of the codomain for the first pair coincides with the domain of the second pair. And in this case, due to free action of the group, there is a unique group element which sends u to y. And then the composition is given by this formula. We just effectively here, what is written here, this can be written as a xy gu gv. Remember that the diagonal action doesn't change the orbit, so this is why we have equality. But now gu becomes equal to y, and then we forget this common y, and then we just write x comma gv. So this is a composition, and the convention I'm using is that the composition is not like for maps, but it is like for fundamental group points of topological space, where we have an endpoint connected to the initial point of the next path, and so on. So this is the convention. And then the identity morphism is this kind of pair. And the inverse morphism is just the exchanging of the components in the pair. And what is worth mentioning about this groupoid is that, so first it is connected, and the group of morphisms for a given automorphism of one given object is isomorphic to the group which we started from. I mean, the group acting freely on the set. So it is now realized as a group of morphisms of one given vertex. And what we are going to do, we are going to apply this to the case when the mapping class group acts freely on the set of decorated ideal triangulations. So we are going now to talk about this groupoid and a theorem due to Hyun dating to 2016 is a presentation of this groupoid. So I'm using now pictorial notation with pairs, like in the previous slide. So we have a set of generators which are transpositions. So remember that our triangles are linearly ordered, so which is the same as enumerated from 1 up to the number. And then the transposition is just the exchange of two indices between two triangles, maybe distant triangles in the some triangulated surface. So ij replaced by ji. So and it is a pair. So in the previous sense, so it is a morphism in this groupoid. And then we have another set of generators corresponding to changes of the marked corners. Corners are marked by a point here. So if we take a triangulation where one marked corner sits here, then if we replace it by a corner here, then this corresponds to morphism rho I. And then the most interesting part of it's the diagonal flips in quadrilaterals tau ij. So if we have a quadrilateral like this, and we replace the diagonal by like this, but remember that the corner should be marked in a specific way to be able to apply these diagonal flips. And but if you want to flip a diagonal in some quadrilateral where the marked corners are not placed properly to be able to do this, then you apply the rho i's to put them where you want, and then you apply this move. So this is how it works. And then so this is a set of generators, and then the set of relations are listed here. So we have just a permutation group for transpositions. Sorry. Then if you change it 3 times the marked corner, you get back to the original situation. So it is order 3. Then the pentagon for the diagonal flips. Then some compatibility relation between corner changes, flips, and transpositions. And a number of trivial relations like commutativity. If you change the marked corner into different triangles, then you can do it in any order. You can likewise you can flip the diagonal in a quadrilateral which doesn't contain a triangle K. Then you can independently change the corner and flip the diagonal. But the transpositions they change the indices of these generators because if they touch and so on, likewise for tau ij. So this is the Hyun's theorem of the presentation of this groupoid. And based on this presentation, so I have a theorem which allows to represent this groupoid by using an arbitrary basic algebraic system. So if we have a basic algebraic system, then we have a canonical projective representation of our groupoid in GL of tensor power of vector v. So here S should read as R. It's the number of punctures. This is the genus of the surface. Where the transpositions go to permutations of the tensor components. The corner changes go to operators R acting in the i's component in the tensor product, and tau ij's flips go to the tij's coming from operator T. And this representation is unitary if V is a Hilbert space and the operators RT are unitary. So in many cases of examples of the quantum dialogue give unitary basic algebraic systems. So in all those cases, the corresponding representations are unitary. So I stop here and thank you for your attention and your patience.
Thank you for the very nice talk. Let me first stop recording.